Okay, so next section, rearrangement of series. So this is how it starts. We have already discussed about it a little bit in the previous video. So the thing here is that that's how Professor Tau starts off. One feature of finite series is that no matter how one rearranges the terms in a sequence, in a finite sequence, the total sum is the same. For example, if one considers a sum of say 5 real numbers which look like this, then you can just simply rearrange the terms in any manner you want. For example, like this, we already know that the sum is going to be the same, and one in fact can prove this very easily by induction on the number of terms in that sum. Now, a more rigorous statement of this involving bijections, of course, has already appeared. One just has to look at remark 7.112, which we already have seen, which of course would involve permuting the terms, and that just comes as a consequence of permuting the suffixes. For example, instead of considering this the suffixes in this order 1, 2, 3, 4, 5, we can permute the suffixes and consider this thing, this permutation 4, 3, 5, 1, 2, which of course can be it can be expressed in terms of a bijection which maps 1 to 4, 2 to 3, 3 to 5, 4 to 1 and 5 to 2. So that's what the author is saying. So the thing here basically is that in a finite sum, it does not matter how we rearrange the terms, the sum is going to be the same. Now the question naturally asks whether the same thing is true in an infinite series. Now it turns out that if all the terms are non-negative real numbers, then the answer is yes. So that's what we are going to see today. So if we are dealing with a series of non-negative real numbers like the ones we considered in the previous section, then we can rearrange the terms. Now the precise statement we are now going to see, and we are going to prove that. So if all the terms are non-negative, then the answer is yes, and this is stated in this proposition. It's the first item of this section, so 741, and the statement is this: let summation an, where n varies from 0 to infinity. If you want, you can take something else here also, some other integer. It does not matter, nothing will fundamentally change. This be a, but taking 0 just makes things somewhat simpler to write and state. Let this be a convergent series. Of non-negative real numbers. And the statement is that if we rearrange the terms of this series, then the rearranged series will continue to be convergent and will have the same sum as the original series. But we have to, of course, state that rigorously using bijection. So this is how it then next goes. Of real numbers, it doesn't stop here. And let f from the set of natural numbers into itself be a bijection. Then this series a f of m, where m also varies from 0 to infinity, is also convergent. You can understand that with this f we are actually rearranging the suffixes. So the suffixes now look like f of m, like how you have here. So the advantage of having the lower limit of the series equal to 0 is that you are now dealing with a bijection on the set of natural numbers. Had you started with some other integer, say m, say here in place of 0 you have a series like this. Sorry. Say you have a series like this. Then rearranging the terms of this series can be brought about by a bijection from this set okay, we cannot because m itself can be negative now. So the set of all integers that n is greater than or equal to m, a bijection from this set to itself. You can state it that way, but it becomes unnecessarily complicated, and since this does not say anything fundamentally different from this situation, so we are just simply taking n equal to 0. Okay, so now let's complete this. Then this is also convergent and has the same sum. That means the sum of the original series equals the sum of the rearranged series. Okay, so let us now prove this. We define, because we are after all going to consider these two series, so first of all we are going to define their partial sums naturally, because convergence or non-convergence depends on these partial sums. We define the partial sums. Let us first define the nth partial sum of the first series. We already know what this is. Summation of that is this finite series, and then the mth partial sum. Let's keep this this variable different from n because they need not be the same. To be the mth partial sum of this series, so it will be a f of m. M varies from 0 to capital M. Since all the AIs, that means all the A's, all the terms of this original series and hence of this series also, because these are after all these only in some rearranged form, they are non-negative. The sequences Sn and Tm are both increasing, and this we have already seen in the previous section when we are dealing with infinite series of non-negative real numbers. Then the sequence of partial sums is an increasing sequence. So the higher, the further you go down the sequence, the larger the terms become. So these are both increasing. Let L be the supremum of the first sequence and L prime be the supremum of the second sequence. Now, from the theory of convergence of such series where all the terms are non-negative, we already know that such a series is convergent if and only if these sequences of partial sums are bounded from above by a real number, and the least upper bound, which is the supremum here, for example this L, is the sum of the series. In fact, that is the limit of the sequence of partial sums, so that is the sum of the series. And we have seen this thing in this criterion, in fact comes from this result from the chapter on limits of sequences, proposition 638. So next we write by proposition 638, L is finite. Why? Exactly how? That is because it's given that this series is convergent. That's already given. So that means its sequence of partial sums should be bounded from above by a real number, and in particular this sequence will converge to its supremum, which then has to also be a real number. So that's how we are getting this conclusion that L is finite. We don't know yet anything about L prime. Now by this proposition again, actually we have to show that L prime is also finite, because that would then imply that this second series is convergent, and additionally we need to show that L is in fact equal to L prime, because that would imply that these two sums are equal. In fact they are. One of them is L and the other now we will show that the other will be equal to L prime, and then we will show that they are equal. So next we write, so by by that same proposition, we are done if we show that L prime is finite and L is equal to L prime. In fact, this is a consequence of this equality. If you just you are able to show that L is equal to L prime, that would automatically imply that L prime is finite. Okay, so now we concentrate on this sequence, the sequence of partial sums of the rearranged series, because we want to say that it is bounded above by some real number, and hence L prime will be finite, and then we can proceed from there. So that's why we arbitrarily fix this capital M. M is any natural number, so but we are going to fix this. So fix M to be a natural number, and let Y denote the set of all natural numbers which are less than or equal to this M. Okay, then by the laws for finite series, the laws of finite series that we already saw in the first section of this chapter, and that thing is proposition 7.1.11. Then by proposition 7.1.11 we have, okay, Tm. By definition, Tm is what? Tm is this finite series summation a f of n, where m varies from 0 to capital M. By using one of the parts of this proposition, which has all the parts where we have the basic properties of finite series, by one of those properties, this series is also equal to this finite sum M, where M belongs to Y. Because you see, in Y what we have, we just simply have all the natural numbers starting from 0 and ending at M. And this series is also by definition just that, where M varies from 0 to M. So by one of the parts of this proposition we have this equality. Okay, but next, this thing is equal to, it can be written as An, where n varies over f of y. You can understand this in a very natural manner, because you see, what are the things, what are the suffixes that are appearing here? You are varying m over y, that means you are varying m from 0 to capital M, and in the suffix you are considering f of m. So instead of doing that, if you apply f on y itself, then you are in fact having the set of all f of m's, and then on that set if you vary n, then you are getting the same thing. But of course this thing follows from again one of the parts of proposition 7.1.11, and in order to be able to do that this step from here to here, you are in fact able to use one of the parts of this proposition. In order to be able to do that, you need to notice that there is a bijection between y and f of y, and f in fact itself gives us the bijection. So we write within brackets, note that f from y to f of y is a bijection. Oh, and why is that true? That is because you see, what is f originally? F is a bijection, that means a one-to-one onto function from n to n, right? Now when you restrict f on this subset y of n, because after all y is a subset of n, when you restrict f on y, the restriction of a one-to-one function is automatically one-to-one, and when you take the second set to be the image of the function itself, image of the function on this set, then automatically this becomes onto. So that is why this is both one-to-one and onto, and hence it is a bijection. So that's why you are able to write like this. So all the things, all the parts of this calculation are now justified. So we can now move on. Okay. Now how do the elements in f of y look like? They are f of m, right? That means, and that also there m varies from 0 to m. So actually we are dealing with a finite sequence of real numbers. These real numbers being natural numbers in fact are somewhat special, that they are not just real numbers but natural numbers. However, that does not have anything to do with what we are going to write next. So this is what we next write. Since f of m, where m varies from 0 to m, is a finite sequence, a finite sequence of real numbers. After all, it does not matter that these terms f of m, the individual terms, are in fact natural numbers. That does not play any role here. The thing is that they are all, after all, all of them are real numbers. So since this is a finite sequence of real numbers, it is bounded. In particular, there exists a natural number n such that f of m is less than or equal to n for all m less than or equal to n. For all m less than or equal to m means for all natural numbers m less than or equal to m. Okay, now when we say that a finite sequence of real numbers is bounded, and they always are, this upper bound in general is a real number, but because we are dealing with in particular natural numbers, so the upper bound can be chosen to be a natural number. And in the general case also this is true. If you are say here, if we were dealing with say real numbers where these are not necessarily natural numbers, then also you will get a natural number upper bound, because the natural numbers are not bounded above. So if there is a real number upper bound, then you can find a larger natural number by the Archimedean property. So there will always exist such an n which is a natural number and which acts as an upper bound for all these f of m. Now this has a consequence which is useful to us. This implies our set f of y is a subset of this set of all natural numbers less than or equal to n. This is a crucial conclusion, because whatever we are next going to write, that heavily depends on this conclusion. So we need to understand why this is true. You see, okay, why is it true and how is it following from these inequalities? You see, when we are considering this set, what are the elements in this set? In this set, we have all the natural numbers starting from 0 and ending at n. And here what we are saying, that f of m, all the f of m are natural numbers less than or equal to n. So any such f of m will automatically lie in this set, because it is greater than or equal to 0 and less than or equal to n. So that is why f of y, whose elements are just precisely these f of m's, is a subset of this. Oh, I need that part, at least this thing, t of m is equal to this. Hence, by proposition 7.1.11, I think it is. These numbers I am never able to remember. 7.1.11. And the assumption that all the AIs are non-negative. We have, okay, now we are going to directly use this, the whatever we have got here in this part of the calculation, we are going to directly write that Tm is equal to this, summation of an as n varies over f of y. Now because this is a subset of this, so if we write another such sum where n does not just vary over this subset but over this entire set, then likely we are considering more values of n than this one. Likely I say because it may happen that these two are equal, but it may also happen that this is a proper subset of this. If this is a proper subset of this, then we are of course having more values of n here than we have here. So now what I am going to write is that this finite sum is less than or equal to the sum of an where n varies over this set. The question is, how is this less than or equal to this? Fine, here we may have more n, so that means there are more an's, more terms here. However, not just any term, non-negative terms. So that's why we have this inequality. And well, of course, these are just some simple explanations for these steps, but we are in fact able to write these things rigorously by applying the various parts of proposition 7.1.11. So that's why we mentioned that here. Okay, now again by another such part of this proposition, this thing, this sum is also equal to this finite series an, where n now varies from 0 to n. It's just a simple thing. This is also one of the parts of this proposition, and this thing is nothing but Sn. If you look at how it looks, so that means we have proved that every Tm is less than or equal to some Sn. That means for every natural number capital M, there exists a natural number capital N such that Tm is less than or equal to Sn. In fact, let us write this thing explicitly. Thus, for every natural number M, there exists a natural number N such that Tm is less than or equal to Sn. Tm is less than or equal to Sn. And why are we able to write for every M? That is because you recall in the beginning of everything we fixed M, but that capital M was arbitrary, any natural number in N. Since L is the supremum of our Sn sequence, this implies Tm is less than or equal to Sn, which is less than or equal to L for every m belonging to n. This n of course depends on m, but the thing here to be noted is that the intermediate Sn is not that important. Now we need to see the thing is that Tm is less than or equal to L for every n. Hence L is an upper bound for this second series of partial sum. Second sequence of partial sums. So which automatically tells us that this sequence is bounded above by some real number, so it is convergent because it is already monotone increasing, and that comes from that proposition 638. And its limit, which is nothing but its supremum, which we are denoting by L prime, should be less than or equal to L, because L is some upper bound but the supremum is the least upper bound. L is an upper bound. So this implies L prime is less than or equal to L. And note one thing, that because we are dealing with a sequence of the sequence of partial sums of a series of non-negative real numbers. So all these Tm's themselves are non-negative real numbers. So their supremum, which is L prime, whatever it is always greater than or equal to 0. But now that we have proved that it is less than or equal to L, where L itself is a real number, there is no option for L prime to be equal to plus infinity. So L prime also has to be a real number. And here itself you can conclude that the second series, the rearranged series, is convergent. And in fact, let us just write that, let us make that conclusion here itself. So L prime is a real number, i.e. the series summation a f of m is also convergent. Okay, now next we need to show that they are actually equal. So by a similar argument with Sn. So by a similar argument means you then switch the roles of Tm and Sn, these two sequences. So whatever calculations we went through where we started with Tm, a similar calculation can be carried out starting with Sn, and in place of f, the bijection f, we can consider the bijection f inverse. Note that f inverse, because f is a bijection, its inverse first of all exists, and the next thing is that the inverse itself is also a bijection. So the author writes with the bijection f inverse instead of f, we will get the opposite inequality, that is L will be less than or equal to L prime. In fact, this part actually is just simply what Professor Tao has mentioned but has not shown explicitly, the calculations. What I want you to do, I want you to actually carry out the steps and make, you just supply the details so that you can see exactly how this thing is also true. It may seem like an unnecessary exercise, but it is not unnecessary, because when you start considering f inverse, there are some subtleties. Okay, so you try to deal with those things on your own. However, if you don't get it, then please let me know. So we get this. Hence, L is equal to L prime, and that proves everything. Not only have we shown that the rearranged series is convergent, but we have also managed to show that it has the same sum as the original series. Okay, so now to illustrate this thing, we have this example. Example 742. From having seen the proof, we become convinced that okay, the result is true. However, when we look at the statement, even now also, it is not immediately apparent that it should be true, and that's the beauty of it. I mean, you just think of it, you have a series of real numbers. Of course, all the terms are non-negative, but still, it does not matter in what way you arrange the terms. In whatever way you do that, if the original series is convergent, then the rearranged series is also convergent. Convergence is not lost. And what is more striking is that the sum is the same, which if you think about it, it's if you just simply think of it, it's unlikely that that should be the case. That is because what is the sum of a series? The sum of a series is the limit of its sequence of partial sums whenever the limit exists. Now, rearrangements will drastically change the sequence of partial sums, but still, not only do you still have convergence, but the limit is also the same. So that is really nice, and something which at first glance it seems like it is not true. It seems like that. However, that's not the case. It is true. From corollary 737, we know that the series summation 1 over n square, wherein varies over all the positive integers. We are going to write quite a few terms in this series because we are going to show one of its rearrangements. So we need terms. Five squared, 6 squared, and so on. We know that this series is convergent. So it's that corollary from the previous section which tells us precisely when this type of series is convergent. It's that thing, namely when q is greater than 1, that is precisely when this will be convergent. For other cases it is divergent. So q equal to 2 gives us this. So this is a convergent series. So now by the thing that we have proved now, we can rearrange the terms. Thus, if we in particular interchange adjacent terms to obtain the series. Interchanging adjacent terms means this. The word adjacent has not been used in the text, but I am just simply writing it to make it more clear. So you interchange 1 over 4 and 1, then you interchange 1 over 9 and 1 over 16, and then let's write 2 more. Then it is still convergent. And has the same sum as the original series. Which, however, we don't yet know what the actual sum is. That is a different matter altogether, but the author does mention this thing. It turns out that this sum has the value zeta of 2. Of course, if you recall, we thought of this series as a function of q. Okay, so when you put q equal to 2, you get this series. So that is zeta of 2. But the thing is that here the sum is actually pi square divided by 6. And this is the fact that we will prove in analysis 2. Once we complete analysis 1, we are now going through analysis 1, the first volume of Tau's analysis series, right? So there is an analysis 2 also. So there we are going to prove this. And the actual result is this effect that we will prove in exercise 16.5.2. So we are still far away from this, but we will eventually reach this. So these type of things will necessitate us to first of all deal with trigonometric functions. We have to, because you see in this text we are doing everything rigorously, right, from scratch. So we will actually have to define pi somehow that does not involve the a circle, that is, you divide the diameter of a circle by you divide the circumference of a circle by its diameter and you then define that ratio to be pi. No, we are going to define pi in an entirely different way. However, we will show that it is actually equal to that pi, and with that definition one can prove that this series sums to this, or any rearrangement of this series. For example, this one also has the same sum. Okay, so let us finish the things here itself. Let's end the video here itself. In the next video, which is coming on next Monday, we are next going to generalize this to series where the terms are not necessarily non-negative. You may have negative terms, however, we will need one condition, that is absolute convergence. If your series does not necessarily have only non-negative terms, but it is absolutely convergent, then again this result is true. You can rearrange its terms and the rearranged series will still be absolutely convergent and its sum will be equal to the sum of this original absolutely convergent series, and then the section will be over. And after that we have our familiar root test and ratio test, which are very heavily used to test for absolute convergence. When a series is given, you can test whether it is absolutely convergent or not. So the most frequently used tests are root test and ratio test. There are many other types of tests which, however, have not been dealt with in this text. So we will see all these things, and so this is all about real analysis. And this coming Tuesday, because we have already reached graph theory once again, so that means we have to again come back to the beginning of the cycle of things. So this coming Tuesday we are again going to see group theory from Einstein's topics in algebra. So until that happens, this is me, Lucifer, from a mathematical room. Have a nice night.